Good morning! Looks like we have audio and video and the stream is up and running, no drop frames. All right, it's about time to start. And I'm just going to send out all of the standard messages. You go out. All right, so got all the messages out. Let's remember where we were. So bring you over here. Let's go to GitHub. Learning Rust. Okay, so currently at chapter 4.2, mutable references. Also, as changes in the last since yesterday morning, Felix or F-Shoot here gave a pull request to the chapter 3 project 12 days. So what he did was he basically came in here and changed it so that to change the type to like be explicit about how long it was, and also to use the enumerate with the iterable, and that allows us to actually like go through and loop through them the way that I had wanted to previously, because now in my for loop I can get the I and the day. And if you remember, I had tried to do that before, but it just didn't work because it wasn't there. It was the enumerate that we needed to get that to work. And what's really awesome is that he also left these explanation comments in here to sort of like explain what is going on with the code to make it work this way. So super awesome. Thank you very much. We also changed these to constants, like true constants, because that's the kind of what they are. All right, so thank you again for helping out there. I have created a contributors section of the README, so you are now the first contributor, as in contributed code in here. Okay, so with that, let's move on to chapter 4.2. I also realized that I want to set up my chat here. If you are in chat, feel free to say hi, or if you're watching a VOD, also feel free to leave a comment and say hi. All right, we got that there. Preview is still working and is muted. Perfect. All right, so let's go find my code. Documents, projects, mine, learning Rust, chapter 4. All right, so here we are in chapter 4. Let's also go to the book. Rust book, version 2, chapter 4.2. And let's go find the mutable references. Here we go. Okay, so we can fix the error in the code from listing 4.4. Okay, so that was yesterday. I need to look at this again. All right, so what was this? This was letString. So create an actual string. We call change and we lend it s, and then we try to push to it. But of course, pushing won't work because we've got essentially a read-only copy, because it's not sending like the length or anything, so it's immutable. Okay, so we can fix the error in the code from listing 4.4 with just a small tweak. So let's see what we have here. Let mute s equals string from hello, change, and then we say like, okay, we're gonna mute s, so we tell it that, and then in here we have to take in, oh, it's mute and it's a string. So that's what it is. Now we can push to it. First we had to change s to be mutable. Then we had to create a mutable reference with, well, reference mute s, and accept a mutable reference with some string mute string. But mutable references have one big restriction. You can only have one mutable reference to a particular piece of data in a particular scope. This code will fail. Okay, so like R1 can't be muted like reference to mute s, and R2 cannot be referenced to mute s. So if I have like I don't actually know if Rust can do an asynchronous function, but I know they can do threads. So I wonder if that's gonna like come into effect there, where I can't like pass the same thing to two different threads, because then they would both be able to update it. Okay, and this one gives the error, cannot borrow s as mutable more than once at a time. All right, that totally makes sense. The restriction allows for mutation, but in a very controlled fashion. It's something that new Rustaceans struggle with, because most languages let you mutate whenever you like. The benefit of having this restriction is that Rust can prevent data races at compile time. A data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access the same data at the same time. So yeah, because like they could both be updating it potentially. At least one of the pointers is being used to write to the data. There's no mechanism being used to synchronize access to the data. Oh, right. So if we're sort of like writing, we want some kind of asynchronous thing. But if we have something to synchronize it, I would guess that there's a way to write it with like just more functions, maybe a third function, and then that is the one that's gonna get the mute s. Okay. Data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. Rust prevents this problem from happening because it won't even compile code with data races. As always, we can use curly brackets to create a new scope, allowing for multiple mutable references, just not simultaneous ones. Well, right, because if we do this, like where we just create a block and it's just in the middle of nowhere, as soon as this block ends, it's out of scope and this variable gets destroyed. So R1 and R2 never exist at the same time in the same scope. But they don't really say. A similar rule exists for combining mutable and immutable references. This code exists in an error. Well, so this should just be a pointer to the location in memory with how large it is. But I guess because this could potentially change that, and R1 probably doesn't update, it just knows how large it is and pointer to it. Cannot borrow s as mutable because it's also borrowed as immutable. Okay, so that's the problem, is that these ones are no longer trustworthy. But I want to try the opposite of this. So let's try borrowing with a block. I think playing with strings, I'm gonna do cargo new binary borrowing and cd borrowing code. Okay, so here's my thought about this. Is if we have let my, I guess we'll just do like the exact same thing. So let string from hello world. And so under normal circumstances, I can do let s1 equals and then borrow. Is it borrow? Am I borrowing mutably? I can't remember anymore. Yeah, I'm borrowing mutably s. So mute s. So if I do this, cannot borrow immutable local variable s as mutable. What am I? Okay, so string. Oh no, that was working. Let mute. Oh, all right. I have to tell it on this side, you're immutable too. And of course, it's going to yell at me if I'm not actually mutating it. So unused variable, and then of course I can like print line, which this one will work if I just do like S1. So cargo run. So hello world, exactly as we thought that it would be. But what and then if I try to repeat this, so let s2 equals and mute s. Obviously this is going to have a problem because it's going to say cannot borrow s as mutable more than once per time. Now, if I repeat the exact sort of experiment they did, which was I have a block here and I save this, suddenly this works, but S1 is no longer in this scope, so this now needs to be S2. And this does warning unused variable. Okay, that's fine. But it does work. If I reverse this, S1 should now be in the same scope as S2, and this should fail. If I just do this. Cannot borrow more than once per time. Yeah, because it's moving into the same scope, so it's unique here, but it's not unique anymore in here. And then back to here, it's unique again. So this scope becomes invalid because of the attempted to borrow twice. So invalid as s is borrowed mutably twice. All right, so I'll save that. Let's continue on. Whew. We also cannot have a mutable reference while we have an immutable one. Users of an immutable reference don't expect the values to suddenly change out from under them. However, multiple immutable references are okay because no one who is just reading the data has the ability to affect anyone else's reading of the data. Even though these errors may be frustrating at times, remember that it's the Rust compiler pointing out a potential bug early, at compile time rather than at runtime, and showing you exactly where the problem is, instead of you having to track down why sometimes your data isn't what you thought it should be. I think it can be interesting here because there's been times that I've abused that in other languages where I've used the references to be able to update places in memory without having to take up extra memory, essentially. So you have large objects and you're just like passing them around and causing side effects everywhere, and everything works fine. It's of course a terrible practice, but it's something that works. And so I could see getting into the habit of doing this Rust way is definitely going to help me also in these other languages where I could be tempted to do it sort of the cheaper way, but but is more expensive in debugging and other potential bugs in the long run. All right, dangling references. In language with pointers, it's easy to erroneously create a dangling pointer, a pointer that references a location in memory that may have been given to someone else, by freeing some memory while preserving a pointer to that memory. A pointer that references a location memory that may have been given to someone else by freeing some memory while... I'm having trouble with that sentence. Pointer that references a location in memory. So if we have like the table in memory, it goes just to one thing that may have been given to someone else by freeing some memory while preserving a pointer to that memory. Oh, is it talking about like it deallocates a memory spot, but there's a pointer to that memory spot? So now the pointer in like C would still work, but it gives you really, really crap data or someone else's data. Let's try to create a dangling reference, which Rust will prevent with a compile time error. Okay, so let reference to nothing equals dangle. Dangle returns a reference to a string. Oh, right, because so this string, they created right here, we're returning a reference to it, but at the end of this scope, this S will be destroyed. It'll be cleaned up from memory. So it's tempting to return an S, but missing lifetime specifier. So that's exactly the problem that I was running into earlier on when I was trying to do this. This error message refers to a feature we haven't covered yet, lifetimes. We'll discuss lifetimes in detail in chapter 10, but if you disregard the parts about lifetimes, the message does contain the key to why this code is a problem. Right, this function's return type contains a borrowed value, which is here, but there is no value for it to be borrowed from because this has been deleted, it's been removed from memory. Let's take a closer look at exactly what's happening at each stage of our dangle code. So, all right, so dangle returns a reference to string. Yep, we got all that. Because S is created inside dangle, when the code of dangle is finished, S will be deallocated, but we try to return a reference to it. That means this reference would be pointing to an invalid string. That's no good. Rust won't let us do this. The solution here is to return the string directly. Right, of course, because then it would stay in memory. This works without any problems. Ownership is moved out and nothing is deallocated. Right, because if we take a look at the original, this would now own the string, or rather, the reference to nothing variable would now own the string and do whatever it wants with it. The rules of references. Let's recap what we discussed about references. At any given time, you can have either, but not both of, one mutable reference and a number of immutable references. References must always be valid. Next, we'll look at a different kind of reference, slices. All right, so let's head over here. We're going to 4-3 slices. Another type of data that does not have ownership is the slice. Slices let you reference a contiguous sequence of elements in a collection rather than the whole collection. Here's a small programming problem. Write a function that takes a string and returns the first word it finds in that string. If the function doesn't find a space in the string, it means the whole string is one word. So the entire string should be returned. Let's think about the signature of this function. Okay, so write a function that takes a string and returns the first word it finds in the string. So yeah, it's going to take in this S type string, and we're getting a reference to the string. And we're going to return. So yeah, that's a, like, I would initially think of, well, we can just return a stir of the string that we found, like create a new thing. But I think that we're going to create, like, pass back a part of an array or something. Maybe a part of the string. This function, first word, has a reference string as a parameter. We don't want ownership, so this is fine. But what should we return? We don't really have a way to talk about part of a string. However, we could return the index of the end of the word. Well, wait, index of the end of the word? Let's try that as shown in listing 4.5. Okay, so we have taken string, let bytes equals s as bytes. So is that counting the bytes, or is that each character? I want to look up as bytes. So, oh, I was already in Firefox. Okay, Rust as bytes. Okay, into bytes, as bytes. Returns a byte slice of this string's contents. Example. Okay, so we're getting, like, the actual byte codes for it. So that's what we're getting there. So we'd be getting that and then searching for the space code. Ooh, so here's this for loop that has this enumerate in it. For I and the reference to the item in bytes iterator enumerate, if the item equals, so this is interesting. I'm not seeing like be created. So is that the byte of space? Is that something that I can actually do? I don't think there's no interactive Rust shell, right? So cargo, oh, I'm in borrowing still. I need to. Cargo, new binary. What is this chapter called? Or what is the subchapter called? It's slices. You are done. And let's code you. Oh, I got the wrong one. I need to cd into it for. Okay, there we go. So now source main. I kind of want to just try print line this with b. I want to see if it's going to print out like the actual bytecode or if it's going to convert that. So cargo run 32. Yeah, so this is the later. This is the bytecode for space. So I guess that's a way to convert it. So converting space to bytes. All right, and then return the index. That feels like it's the equal sign. So we're returning the beginning. I feel like what they wrote here is not exactly what this is doing. This is doing the beginning of it. Wait, can I play this? Oh ha, it's not being passed in everything, so. The first, let's see. Let's break down this code a bit, because we need to go through the string element by element and check whether a value is a space. We'll convert our string to an array of bytes using the asBytes method. Next, we create an iterator over the array of bytes using the iter method. So that's what we do right here, yep. We'll discuss iterators in more detail in chapter 13. For now, know that iter is a method that returns each element in a collection, and enumerate wraps the result of iter and returns each element as part of a tuple instead. The first element of the returned tuple is the index, and the second element is a reference to that element. This is a bit more convenient than calculating the index ourselves. Because the enumerate method returns a tuple, we can use patterns to destructure that tuple, just like everywhere else in Rust. So in the for loop, we specify a pattern that has I for the index in the tuple and a reference item for the single byte in the tuple. Because we get a reference to the element from iter enumerate, we use the reference in the pattern. We search for the byte that represents the space by using the byte literal syntax. If we find a space, we return the position. Otherwise, we return the length of the string by using string.length. We now have a way to find out the index of the end of the first word in the string. But there's a problem. We're returning a usize on its own, but it's only a meaningful number in the context of the reference to the string. In other words, because it's a separate value from the string, there's no guarantee that it will still be valid in the future. Consider the program in listing 4.6 that uses the first word function from listing 4.5. Okay, so first word is this. Well, yeah, because word is not really a word, it's going to be a number. So that should be like word position. S.clear, this empties the string, making it equal to empty. Okay. Yeah, that totally is worthless. This program compiles without any errors and also would if we used word after calling s.clear. Word isn't connected to the state of s at all, so word still contains the value 5. We could use that value 5 with the variable s to try to extract the first word out, but this would be a bug because the content of s has changed since we saved 5 in the word. Having to worry about the index and word getting out of sync with the data in S is tedious and error-prone. Managing these indices is even more brittle if we write a second word function. Its signature would have to look like this. Now we're taking in, well, second word. Oh, right, because we're like returning the tuple of two different indices. Now we're tracking a start and an ending index. And we have even more values that were calculated from data in a particular state, but aren't tied to that state at all. We now have 3 unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution to this problem: string slices. A string slice is a reference to part of a string, and it looks like this. Okay, so we have our string. Let hello equals. So I guess it's string, so reference to string, but then we're using bracket notation to get 0 through 5. And world is position 6 through 11. So 0, 1, 2, 3, 4, 5. So this would be the first one. 6, 7, 8, 9, 10. 11 is out here. I guess it's non-inclusive for the end one. Is that what I'm seeing? This is similar to taking a reference to the whole string, but with the extra 0.5 bit. Rather than a reference to the entire string, it's a reference to a portion of the string. The start-end syntax is a range that begins at start and continues up to, but not including, end. We can create slices using a range within brackets by specifying starting index, ending index, where starting index is the first position included in the slice, and ending index is one more than the last position included in the slice. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to ending index minus starting index. So in the case of let world equals reference to s, and then getting a slice of positions 6 through 11, and world would be a slice that contains a pointer to the 6th byte of s and a length value of 5. Okay, and it can do that because that's exactly how it's being stored in, well, either the heap or the stack. Can I do this on strs? I want to try that. So if I come here, this is converting into bytes. I'm going to comment that out. So if I say let hello equals just a standard str, so hello world bang, then I want to get, so let h equals, what is it? It's a reference to hello 0.5. And I'm going to print line h. I don't see any errors popping up, so I'm guessing this is going to be just fine. So cargo run. Hello, okay, so perfect. So yeah, I can do this on strs as well as strings, which is nice to know. We can create slices using a range within brackets, but oh wait, I already read that one. All right, so we show this in a diagram. So yes, like our string is this, and then world, which is a slice of this string, is just a pointer to where this starts. With Rust's ... range syntax, if you want to start at the first index 0, you can drop the value before the two periods. In other words, these are equal. Let is equal string, so like create a string. Okay, so yeah, if we're going from 0, we just do ... because it's assumed that it starts at 0. But if I want to start at above 0, like 1 or 2, I have to put that in there. By the same token, if your slice includes the last byte of the string, you can drop the trailing number. That means these are equal. Okay, so if I want to go to the end. So is it legal to just do ... Like if I wanted to do this, even though it's silly because I'm just really grabbing a reference to the entire thing in here. No error message. Yep, totally legal. You can also drop both values to take the slice of the entire string. Oh, well, they just told me there. Note, string slice range indices must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. For the purposes of introducing string slices, we are assuming ASCII only in this section. A more thorough discussion of UTF-8 handling is in the strings section of chapter 8. With all this information in mind, let's rewrite first word to return a slice. The type that signifies string slice is written as reference to stir. Okay, so because it's a specified portion in memory, we're gonna make it immutable, and it's just a reference to it. That's why it's looking like this. Okay, so we're getting the bytes. We're gonna loop through all of these bytes. If the item matches the byte of space, return, and then it's gonna be a slice from 0, which we could replace with ... to I. And otherwise, we're going to return the entire thing altogether. We get the index for the end of the word in the same way that we did in listing 4.5, by looking for the first occurrence of a space. When we find a space, we return a string slice using the start of the string and the index of the space as the starting and ending indices. Now when we call first word, we get back a single value that is tied to the underlying data. The value is made up of a reference to the starting point of the slice and the number of elements in the slice. Returning a slice would also work for a second word function. All right, so second word. Right, because then like whatever, it's exactly the same because it takes in something new. Uh-oh, my stream health. Stream said it's healthy. My preview window just sort of went bonkers. I'm gonna hit refresh. Oh, and my preview is back. Okay, good. That's good to see. It's always a little bit weird when you look over in a stream preview is just like sort of frozen there. No drop frames, so everything seems to be good there. We'll just continue on. Okay, we now have a straightforward API that's much harder to mess up, since the compiler will ensure the references into the string remain valid. Remember the bug in a program in listing 4.6. When we got the index to the end of the first word, but then cleared the string so our index was invalid? That code was logically incorrect, but didn't show any immediate errors. The problems would show up later if we kept trying to use the first word index with an emptied string. Slices make this bug impossible and let us know we have a problem with our code much sooner. Using the slice version of the first word will throw a compile time error. Oh, right, because we clear it. Well, wait a second. So if we use it, or if we just clear it at this point in time. Cannot borrow s. So borrowing s as mutable. Mutable there. Because it also borrowed as immutable. So we're immutably borrowing it or lending it to first word, but it's immutable here. Mutable borrow. So clear is mutably borrowing s and changing it inside of it. So that's what's going on. Recall from the borrowing rules that if we have an immutable reference to something, we cannot also take a mutable reference. Because clear needs to truncate the string, it tries to take a mutable reference which fails. Not only has Rust made our API easier to use, but has also eliminated an entire class of errors at compile time. String literals are slices. Recall that we talked about string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. So let s equals just the string literal hello world. The type of s here is borrowed stir. It's a slice pointing toward that specific point of the binary. This is also why string literals are immutable. Reference str is an immutable reference. String slices as parameters. Knowing that you can take slices out of literals, and string s leads us to one more improvement on first word, and that's its signature. So in this here, we take in string s, which is a borrowed string or a reference to a string, and returns a reference to a str or borrowed str. A more experienced recitation would write the following line because it allows us to use the same function on both string s and str s. So yeah, we're gonna borrow str, and we remember, like, we found out that we can do this. Like, it's okay to like, it kind of converts or it uses that. Like, you can pass a full string in or a str in. If we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the entire string. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. So yeah, everything just works now. We get our string. First word, we pass it my string, and then we pass it in the full slice of it. It's like the entire one. So that's sort of interesting. That I have seen in like a little bit of the other code that I've looked at, that's Rust, I have seen this pattern happening. So I guess using just the dot dot is a little bit more, is going to be more common than I thought it was initially. Other slices. String slices, as you might imagine, are specific to strings, but there's a more general slice type too. Consider this array. So we have an array of 1 through 5. Just like we might want to refer to a part of a string, we might want to refer to part of an array and would do something like this. Would do so like this. So A, 1 through 5, let slice equals reference to A, 1 through 3. This slice has the type reference I32. It works the same way as string slices do by storing a reference to the first element and a length. You'll do this kind of slice for all sorts of other collections. We'll discuss these collections in detail when we talk about vectors in chapter 38. So yeah, this is just part of, so 0, 1 here, 2, 3. So this is going to be an array of 2 through 4. You know, something I haven't tried is what happens when I try to print a collection like an array. So if I have let my array equals 0, 1, 2, 3, and I print just A, what do I get out? Cannot be formatted with the default formatter. Okay, so it doesn't know how to format it out to the screen. Try using : instead if you are using a format string. I don't think I am. The trait standard format display is not implemented for an array of integers. Okay, so that's the problem, is like it can't do that because there is no way, like built-in way to print out arrays themselves. I could like get a slice of this, so I can, what is it? It's so take a reference to position, let's say like 1 dot dot 1. It does not like that. Integer does not implement standard format display. Oh, I can't do it for an integer at all? Or, oh wait, no, it's still returning an array, isn't it? So it's only if I do like 1 will that work, because then I'm getting a specific 1 out of here. So even if I get a slice of it, it's still a slice of an array. There's still an array there. Completely useless. Completely useless to print line, but useful if I want to get like a portion of an array. So can only print integers, not full arrays. Hey, save. Okay, summary. The concepts of ownership, borrowing, and slices are what ensure memory safety in Rust programs at compile time. The Rust language gives you control over your memory usage like other systems, programming languages. But having the owner of data automatically clean up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust work, so we'll talk about these concepts further throughout the rest of the book. Let's move on to the next chapter and look at grouping pieces of data together in a structure. I'm sort of like sad that there's no challenge at the end of this chapter. I was kind of like hoping that all of them would have that. But that brings us to chapter 5, and it's 7:47, so we got a few minutes. We can at least read the introduction to this, sort of like take a look at what we're going to be getting into. So, using structs to structure related data. A struct or structure is a custom data type that allows us to name and package together multiple related values that make up a meaningful group. If you're familiar with an object-oriented language, a struct is like an object's data attributes. In this chapter, we'll compare and contrast tuples with structs, demonstrate how to use structs, and discuss how to define methods and associated functions to specify behavior associated with a struct's data. The struct, or structure, and enumerator, which is discussed in chapter 6, are concepts are building blocks for creating new types in your program's domain to take full advantage of Rust's compile time type checking. So in something like Java, which is a object-oriented, like class-based language, creating new types is done through classes. You know, you create a class, you create a constructor, you return, and then you can use the new keyword to create objects based upon that. But it's also the type. So you can say like, oh, this object must be of type, whatever the class name is. So it looks to me like this is going to be a way for creating types instead of using classes, which is it's kind of nice. It feels a little bit like, like in JavaScript, you can just create objects just by using, well, hey, I'm just going to create a new curly bracket. Now I have an object now. It sort of feels like I'm going to be able to do that, except with a lot more protection and a lot more sort of structure around it. No pun intended. All right, so let's take a look at the first section in here. 5.1, defining and instantiating structs. Structs are similar to tuples, which were discussed in chapter 3. Like tuples, the pieces of a struct can be different types. Unlike tuples, we name each piece of data so it's clear what the values mean. As a result of these names, structs are more flexible than tuples. We don't have to rely on the order of the data to specify or access the values of an instance. To define a struct, I realize I'm probably in the way of this code down here. To define a struct, we enter the keyword struct and name the entire struct. A struct's name should describe the significance of the pieces of data being grouped together. Then inside curly brackets, we define the names and types of the pieces of data, which we call fields. So I'm used to calling these like keys and values, but fields is fine. So like this is an entire field. For example, listing 5.1 shows a struct to store information about a user account. So struct user, I notice that they're using a capital U here. And they're not mentioning that yet. Okay, so capital user, we have our field, which the first field is username and string, email. So we're giving them the types too. Okay. To use a struct after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct and then adding curly brackets containing the key and value pairs where the keys are the names of the fields and the values of the data we want to store in those fields. We don't have to specify the fields in the same order in which we declare them in a struct. In other words, the struct definition is like a general template or a blueprint for the type, and instances fill in that template with particular data to create values of the type. For example, we can declare a particular user as shown in listing 5.2. So yeah, this is definitely looking very much like basically non-object oriented ability to use, like, get the benefit of the class without the object oriented part, which is nice. I've been getting more into functional programming recently, so this is actually really nice to see. Okay, so we have this, let user1 equals, and then we just call user, no new keyword necessary for this, open brackets, and now it's just standard key value syntax like most, just most languages do. I have noticed a trailing comma in here. And so I want to see, is that trailing comma necessary? Or is it just sort of like whatever you feel like? Okay, so let's go down and we're going to do cargo new binary structs. CD structs and code dot. Okay, so if I want to create a new struct, they didn't say that, so I'm going to just say, I'll just say user voodoo doggies. And we'll have a name, which is going to be, no update. A name which is going to be a, well, do we want it to be a string like this? Probably. And a, I guess we could do age. I'm going to have to make up some of this because I only know like the name of some of the doggy friends that I have. Age is going to be a unsigned 32. They better not be over that. Now if I save, it's only just saying, hey, I'm not using it. I'll need a semicolon. And so now I can say, okay, let dog, or let like Kiki, for example, equals an instance of doggies with name is going to be string from Kiki. Comma, because it's more of like a structure object rather than an actual executable line. And then age is going to be something like, I don't know, I think she's 5. Do that, and now I can print line and say, so Kiki is years old. And I can have Kiki dot name, Kiki dot age. And no doubt I could loop through this and have variables like it's stored into an array and be able to like print these out of a variable here, or out of a loop. So no errors. So I don't think that there's a problem with the commas. That just might be sort of a best practice syntax that people are doing. So cargo run. Yep, everything is just fine. Now, what I have heard and seen in like JavaScript and some other languages that are being controlled in Git is that adding on these commas can be nice, because when you add another line to the end here, it doesn't have this as a removed line and recreated with just the comma. You only see the new stuff and everything else just remains the same. So that could be exactly what the best practice that Rust uses. The only problem that I found in JavaScript is that, well, JavaScript allows it, JSON does not, and use JSON a lot in JavaScript. And it gets kind of annoying. Okay, so we did that. To get a specific value from a struct, we can use dot notation. If we wanted just this user's email address, we can use email user1.email wherever we want to use this value. If the instance is mutable, we can change a value by using the dot notation and assigning into a particular field. So, okay, we mute the entire thing, and now all of them are mutable. Note that the entire instance must be mutable. Rust doesn't allow us to mark only certain fields as mutable. Also note that as with any expression, we can construct a new instance of the struct as the last expression in the function body to implicitly return that new instance. So yep, this is returning a full structure, which basically we're taking in two things and just sort of setting it up. It makes sense to name the function arguments with the same name as the struct fields, but having to repeat the email and username field names and variables is a bit tedious. If the struct had more fields, repeating each name would get even more annoying. Luckily, there's a convenient shorthand. That will be interesting. But we'll be getting to that next time, because it is 7:58. It's almost time for me to start going around about my day. But today has been really awesome. We've gotten through quite a bit, learning about, finishing ownership, slices, and now getting into structures, which is super interesting and will allow us to like build some really awesome stuff. So I'm going to update our README here. So I'm going to save, quit out of this. And we'll update here. Inside the README, we're currently at, what is it, 5.1? We're currently at 5.1. So 5.1, and not at mutable preferences anymore. Now we're about to start using the field init shorthand when variables and fields have the same name. Okay, so we'll be getting back to that, not tomorrow. Tomorrow is the weekend and I'm gonna sleep in. So instead, I am probably I'm gonna be getting to this next week on Monday. So I hope that you all have a great rest of your day and a great weekend, and I'll see you next week as we continue with Rust.